The imidazole ring system, which contains 2 nitrogen atoms, is found in the amino acid histidine. Which statement is true regarding the basicity of the 2 ring nitrogen atoms? So we have some options here. This is going to be a question where we're going to want to take a look at each letter and kind of go through it. So both are strongly basic since the ring is aromatic. This ring is aromatic. Right, these can be put here, and you could go, let me think, here, and you could go there and get a minus charge there. Maybe put a plus charge here. So yeah, there's definitely resonance in there. It's cyclic. Those are pi electrons, so there's 3 pi electron pairs. So it is aromatic. However, what I should say, however, both are strongly basic since the ring is aromatic. That doesn't say much about the basicity. So a compound being aromatic does make it more stable, typically. And we want to look at stability of the conjugate base. So we just don't want to go with A yet. Let's look at this in terms of stability of conjugate base. So I want to show you. Let's first look at the conjugate acid of both of these. So we want the conjugate acid of both of these guys. Show you what we're talking about, right? This, we want basically the histidine side chain, which incidentally I did some research on in the laboratory at Oakland. Professor Chavez. Shout out, I guess. Okay, so H would be a positive charge here. Right, this would be in its acidic form. Right? Okay, so positive charge on both of these guys. Right, so the conjugate base of this guy is this, right? That is group number 1. That's the conjugate base for the first nitrogen. Conjugate base for, I don't want to be in your way, for the second nitrogen is going to be, if this guy lost 1 proton, so lone pair H, this guy's still got here. So this is the conjugate base of the second guy. And whichever conjugate base is more stable shows that that N is the more acidic N, aka the less basic N. So if this guy up here is more stable, then this is the more acidic N, and this is the more basic N. Right, so that's 2. So if this guy, right, let's add our resonance, don't forget about that. If this guy is more stable than this guy, then let's see, this is the stronger acid, number 2, and number 1 is the stronger base. Hopefully that makes sense. We're looking at stability of the conjugate base in order to determine acidity, but we got to look at conjugate base of one group at a time and compare them. Okay, so which of these guys is going to be more stable? So I'm going to get rid of this so we can work out this wording. Okay. Or they could be, right, we could show that they're both strongly basic, both are pretty acidic. We'll see. Okay, so let's look at this conjugate base, which is if just group 1 lost. So this is with group 1 acting as an acid. Okay, so we're here. We are here. This guy plus. So we want to try to stabilize this. Let's just draw these side by side. Or, well, and I guess we want to try for both of them. We want to try to stabilize this guy. H here. So this guy has a positive charge too. Right? If it's neutral up there, add a proton, it's positive. Okay, so let's see if we can. How would we stabilize some of these guys? Well, we'd show that it has resonance forms, right? So this guy up top Well, let's look here first. So this is aromatic, right? So that's good. What we could do is we could go here. We could then go, or which way do I should go? No, I should go. If we go here, and we go here, and we go here. No, we go here, here. We keep that there. Okay. Right, so what we got is we put a double bond here, put a lone pair here, and this. Okay, and so now, look at this. These guys are the exact same compounds, just turned around. So this is very stable, right? This is almost like a symmetric. In reality, this might just be a symmetric molecule. I mean, it has two resonances that are exactly the same with just moving the electrons to the other end. So right, this conjugate base here is very stable due to resonance. So that means that this guy is a pretty good acid, right? Stable over there. So, I'm sorry, the protonate of this. This guy is a pretty good acid, right, to lose that. And so that means that this guy, this number 2, is a pretty weak base. So this resonance form up here, we cannot get rid of this positive charge. Right? This had, I should put, this had a positive charge here, right? Screwing up with that. So this had a positive charge over here now, right? Okay, so we cannot move this, get rid of this positive charge here, because if we go here, we break the octet rule, right? So that can't happen. We already have 1, 2, 3, 4 bonds, so we can't add a double bond here. We have 5 lines going to N, which breaks the octet rule. So there is no resonance form to stabilize this. So let me think. What does that mean? That means that, well, that means that this guy, that means that if this formed, it would pick up an H right away, right, in solution, because it's unstable, so to pick that up, then this guy would lead. So this guy's got to go first. This is the more acidic group, 2, which we showed down here, right? So 1 is more basic than 2.